So, in the last few lectures we were discussing conservation equations in cylindrical coordinates for unidirectional transport. So, in this particular case you have one axis, okay, around which there is the temperature or the velocity field is axisymmetric. Okay. So, I have one axis around which the temperature or the velocity field is axisymmetric, and if I look from above, right. So, if I take this as the x direction, okay, I will have two coordinates in the plane. Okay. So, for consistency let me just take this as z for present. Okay. So, I will have x and y, and in the plane any point that is on the plane at a certain distance r from the origin, okay, at a distance r from the origin, the coordinate is the distance r. Okay. We assume that there is no variation in temperature or concentration of velocity around the axis. The only variation is in the r direction. Okay. So, that is the assumption here, and we had derived conservation equations in this case. For constant diffusion coefficient, these equations are of the form partial t by partial t is equal to alpha by r d by dr of r partial t by partial r. Okay. And so far we had solved solution for the steady state solutions in this case. Okay. So, typically you have an inner and an outer wall. Okay. Typically you have an inner and an outer wall, and you are specifying the temperature on the inner and the outer walls, and you want to find out what is the velocity or the temperature or the velocity fields in between these two. From that find out what is the flux, and thereby relate the flux to the difference in temperature. Okay. So, that was the objective so far for steady state problems, where there is no accumulation in or no source within the domain. Okay. So, that has been the problems that we have solved so far. Now, we will look at unsteady problems, okay, where there is a time dependence. Okay. If you recall, in the Cartesian coordinate system, we had started solving with a similarity variable for diffusion into an infinite medium, okay, for diffusion into an infinite medium. In cylindrical coordinates, the equivalent of that is for diffusion from an infinitesimal heat source placed at the center into an infinite medium with temperature T infinity far away. Okay. So, if I have a source of energy placed at along the axis, if I have a source of energy placed along the axis, that energy is going to get conducted away from the axis. Okay. Okay. So, for more definiteness, let me define the problem precisely. This is heat conduction from a wire of infinitesimal thickness. And the boundary conditions will be that as r goes to infinity, okay, T is equal to T infinity, okay, it tends to a constant temperature far away. At r is equal to 0, the total heat transfer rate is equal to QR. Okay. So, since the wire is of infinitesimal thickness, the temperature in the fluid will be finite only if the heat transfer rate is finite. Okay. The temperature in the fluid will scale with that heat transfer rate, okay, the total heat transfer rate. Okay. And at t is equal to 0, t is equal to T infinity for r greater than 0. Okay. That is, you have a wire in a fluid, say a resistance wire that conducts heat. At t is equal to 0, the temperatures are constant everywhere, and at t is equal to 0, the wire is switched on, so that it generates a constant amount of heat per unit time. Okay. So these are for example, for heating applications, you have high resistance wires which heat up, okay, when you pass a current through them, and the amount of flux that is generated is going to be a constant, is going to be independent of time if the voltage difference and the resistance are constants. Okay. So what we have specified is that the temperature far away. So we are looking at the transient profile. Okay. How does the transient profile evolve with time if you switch on the wire at time t is equal to 0? Okay. What is the rate of transfer of energy? The rate of transfer of energy from the wire is of course equal to a constant QR. Okay. I will define the constant QR per unit length, say. Okay. So heat transfer rate per unit length is equal to QR, and we assume that there is no variation along the z direction in this case. Okay. There is no variation in the z direction in this case. In this case, the boundaries are at r is equal to 0 and r is equal to infinity. Okay. Those are the boundaries in this case. So there is no length scale in the problem. Okay. And therefore one might attempt a similarity transform. Okay. Similarity variable we already know, psi is equal to r by root alpha t, just from dimensional analysis. Okay. It is just from dimensional analysis, psi is equal to r by root alpha t. Okay. Substitute that into the equations. Okay. Partial t by partial r is equal to 1 by root alpha t partial t dt by d psi. Okay. And partial square t by partial r square is equal to 1 by alpha t d square t by d psi square. Okay. Using just chain rule for differentiation. Okay. I will expand this out as the time derivative, the derivative of the temperature with respect to time is partial psi by partial t dt by d psi. Okay. Partial psi by partial t, psi is given by this. Okay. So this becomes equal to minus r by 2 root alpha t power 3 by 2, okay, dt by d psi. And r by root alpha t is just equal to psi itself. So, I will get minus psi by 2 t, okay, dt by d psi. Note that I have not yet scaled the temperature here. Okay, I have not yet scaled the temperature here. The reason is that I do not have a temperature at the surface of the wire. Okay, I do not have a temperature at the surface of the wire. I have only a flux. Okay. Therefore, what I can do is to define T star as just equal to T minus T infinity, okay. Okay, just a difference between temperature and far field temperature. So, that this corresponds to T star equals 0 and this corresponds to T star equals 0. Okay. So, I just subtract out the far field, the temperature at infinity from this, okay. And I express everything in terms of T star. Okay. Since I have derivatives of temperature, the derivative of T infinity will be 0 because it is just a constant, it is not a function of position, it is the temperature far from the wire. Okay. So, therefore, I can express everything in terms of T star here. Okay. And let me write that T star is equal to T minus T. Okay. So, substituting these into the equations, okay, into the conservation equation, okay, into this conservation equation, minus psi by 2 t dt by d psi is equal to alpha by alpha t d square plus the second term here, which is alpha by r into the first derivative. So, I will just get alpha, once again you can easily verify, you will get alpha t into psi dt by d psi. And these alphas will all cancel out, t will all cancel out. The equation is only a function of the equation is only an equation in psi and not independently in r and t. Boundary conditions, r goes to infinity implies that psi goes to infinity. Okay. R is equal to 0 means that psi is equal to 0 and t is equal to 0. Okay. If t is equal to 0 and r is finite, then psi is equal to infinity, psi goes to infinity. Okay. So, recall that in the case of heat transfer in one dimension as well, we had two boundary conditions and one initial condition, and when we expressed the boundary and initial conditions in terms of the similarity variable, one of the boundary conditions as r goes to or as z goes to infinity was the same as the initial condition at t is equal to 0. So, in the transformed coordinates we had only two independent boundary conditions. The same situation applies in this case. Okay, you have only two independent boundary conditions. Okay. So, this is the equation. Okay. So, if I multiply throughout by t and I take one derivative to the left hand side, I will get minus of psi by 2 plus 1 by psi dt by d psi is equal to d square t by d psi square. Okay. So, that is the conservation equation subject to boundary conditions, and I will rewrite the conservation equation and the boundary conditions here. Okay. And the boundary conditions are as psi goes to infinity, T star is equal to 0, as at psi is equal to 0, the total heat transfer rate per unit area, okay, per unit length is equal to QR. Okay. What is the heat transfer rate per unit length? Okay. The flux QR is equal to minus K times partial T by partial R, okay, is equal to minus K by K by root alpha T, okay, dt by d psi. Okay. This is the flux. Okay. Heat transfer rate per unit length is equal to 2 pi r into qr. Okay. So, if I take a small distance, okay, in the limit as r goes to 0, the heat transfer rate per unit length perpendicular, okay, the heat transfer rate per unit length perpendicular has to be equal to 2 pi r times this, okay, 2 pi r times qr. Okay. So, this has to be equal to 2 pi psi root alpha t into qr, which is minus k by root alpha t dt by d psi. Okay. And the square root of alpha t will cancel out, and I will get minus 2 pi k psi dt by d psi. Okay. This has to be equal to the heat transfer rate per unit length. Okay. In the limit as psi goes to 0, okay, as you go towards the wire, in the limit as psi goes to 0, this psi times dt d psi has to be finite, okay, has to be a finite number, and that has to be equal to the heat transfer per unit length perpendicular to the wire per unit time. Okay. So, that is the condition that has to be applied. Okay. The flux the total heat transfer rate condition that has to be applied in the limit as psi goes to 0. Okay. How do we solve this? Okay. We had seen this earlier. We write W is equal to dt by d psi. Okay. Then you will get minus psi by 2 plus 1 by psi to W is equal to dW by d psi. Okay. You will get minus psi by 2 plus 1 by psi d psi is equal to dW by W. Okay. Minus psi square by 4, okay, minus natural logarithm of psi is equal to natural logarithm of W. Integral of 1 over psi is log psi, okay, and therefore, you can exponentiate this and you will get that W is equal to 1 by psi e power minus, so there should be a constant of integration here. Okay. So, I should Okay. So, if you exponentiate the constant of integration, you get another constant. Okay. So, you will get this as W is equal to C by psi e power minus psi square by 4, okay, and this is equal to dt by d psi. Okay. Which implies that T is equal to C integral. Okay. The upper limit has to be psi, the lower limit it cannot be 0, because at 0 we do not know what the temperature is, we know only what the flux is. Okay. So, the lower limit cannot be 0, okay, we know only the flux at the lower limit. We can take infinity as the lower limit, because we know what is the temperature there. Okay. We know what is the temperature at infinity, that has to be 0. Okay. So, this dummy variable divided by psi prime e power minus psi prime square by 4. Okay. That is the final expression. Okay. How do we determine the constant? From this condition. From this condition. Okay. So, from this condition we know what is dt by d psi, we just substitute that here 2 pi k psi, okay, into dt by d psi is c by psi e power minus psi square by 4 is equal to qr. Okay. Substituting from this expression, okay, substituting from this expression, and you can see that I had to impose this in the limit as psi goes to 0. Okay. And in the limit as psi goes to 0, you can see that these cancel out and you actually get a finite value for this heat transfer rate. The flux is actually infinite in this case. The flux goes as 1 over psi, so it is infinite, but the surface area goes to 0 in such a way that the heat transfer rate per unit length is finite, and that has to be equal to qr. Okay. And in the limit as psi goes to 0, this exponential here becomes equal to 1, okay, and therefore I get the result that C is equal to minus qr by 2 pi k. Okay. C is equal to minus qr by 2 pi k. Okay. And therefore, the solution for the temperature field T star is equal to minus qr by 2 pi k integral from minus infinity to psi. Okay. Note that in this expression I should have had another constant of integration. I should have had another constant of integration, right. When I integrated once, you should get one constant of integration. That constant of integration was fixed from the condition that T star is equal to 0 as psi goes to infinity. Okay. The right side you can see here, it has to be go to 0 as psi goes to infinity because the upper and lower limits of integration are the same. Therefore, T star is equals to 0 as psi goes to infinity fixes that second constant of integration to be 0 because T star is equal to 0, okay, as psi goes to infinity. That is the reason I had taken the lower limit of integration as infinity, okay, so that as psi goes to infinity T star is equal to 0. Upper limit should be the variable, okay. Upper limit of integration, when you take the integral of a derivative, the upper limit of integration should always be the variable itself. The lower limit should be fixed in such a way that it satisfies the boundary condition at some boundary. We do not have the temperature at psi is equal to 0, we have only the flux. We do have the temperature at as psi goes to infinity, that has to be 0. Therefore, if I choose the lower limit as infinity, the result becomes 0 as it should be from the boundary condition as psi goes to infinity. So, this is the solution for the temperature field. Okay. If I plot this, okay, you can see that the temperature field itself will go to infinity. Okay. Okay. So, if I plot psi versus T of psi, okay, it goes to 0 far away, it goes as e power minus, it goes as e power minus psi square by 4 divided by psi, the integral of that, okay, it goes to 0 far away. As psi goes to 0, this thing actually diverges. Okay. This diverges as the logarithm of psi. Okay. This diverges as the logarithm of psi, okay, because as psi goes to 0, right, as psi goes to 0, this term here, okay, becomes goes to 1, and I have integral of d psi by psi, and that will go to infinity. So, the temperature itself goes to infinity, the heat flux also goes to infinity. Okay. Note that the heat flux is given by qr is equal to minus k dt by dr. Okay. Okay. And this is equal to minus k by root alpha t, okay, dt by d psi. And dt by d psi is given by this expression here, okay, minus k c by psi root alpha t. Okay. e power minus psi square by 4. Okay. This is the heat flux. Heat flux at the wire surface goes to infinity, the temperature goes to infinity, the surface area around the wire goes to 0 as psi goes to 0, in such a way that the total heat transfer rate is finite. Okay. In such a way that the total heat transfer rate per unit length of the wire is finite. Okay. So, that is the solution in cylindrical coordinates. Okay. In cylindrical coordinates, since the wire is of infinitesimal thickness at the axis, okay, it is of infinitesimal diameter at the axis, it is effectively a delta function source in 2 dimensions. Therefore, the temperature goes to infinity, the flux goes to infinity in such a way that the total heat transfer rate per unit length remains finite. Okay. So, that is the solution in 2 dimensions for the heat transfer from a wire. Okay. And this function actually decreases pretty fast. Okay. The solution for example, this one is equal to 0.01 for example, okay, for psi is equal to 3.26, okay, or r is equal to 3.26 times root of alpha t. Okay. So, that square root of alpha t is a penetration depth of the heat flux into the fluid surrounding the wire. Okay. In this particular case, the temperature does go to infinity from the solution. Okay. It goes as integral of 1 over psi. The heat flux goes as proportional to 1 over psi as psi goes to infinity, in such a way that the heat transfer rate is a constant. This solution can always be applied provided the thickness of the wire is much smaller than the penetration depth. Okay. Okay. If the wire was actually a finite wire with some diameter d, okay, so long as d is much smaller than root of alpha t. Root of alpha t is the penetration depth of the temperature field into the wire after the heating has been switched on. So long as d is much smaller than square root of alpha t, the wire looks like an infinitesimal source of heat. Okay. So long as the penetration depth is much larger than the diameter, the wire looks like a source of heat of infinitesimal thickness. So, this condition is that d square is much less than alpha t, or t is much greater than d square by alpha. Okay. When the time is much larger than the ratio of the diameter of the wire square divided by alpha, and you do not have any external boundaries. Okay. So, the approximation we made was conduction into an infinite medium. Okay. If you had a finite medium, okay, if you had a finite medium of some diameter, let us say d of the d, and the diameter of the wire was equal to dw, say. Okay. Then this is valid so long as the penetration depth is much larger than the thickness of the wire, but it is much smaller than the outer diameter d. Okay. So, so long as the penetration depth is much larger than the thickness of the wire, but much smaller than the outer diameter d, I can use this condition. Okay. Or when dw square by alpha is much less than t is much less than d square by alpha. At very early times, the penetration depth is comparable to the diameter of the wire, and I cannot assume it is of infinitesimal thickness. In the long time limit, the penetration depth becomes equal to the diameter of the vessel, and then once again I cannot use this similarity solution. Only at intermediate times I can use this similarity solution to find out what is the heat flux from the wire and the temperature evolution in the fluid. So, this is the similarity procedure for a cylindrical coordinate system, more restrictive than for a Cartesian coordinate system, but nevertheless it can be used if you have transport from an infinitesimal wire into an infinite medium. So, we will continue on to the next topic, that is the use of separation of variables in a cylindrical coordinate system. That will be our next topic, and I will continue this in the next lecture. I will see you then.